Welcome to Paris Podcast number 115, and today we're talking about drag reduction systems for Formula Student cars. So, drag reduction systems are systems that reduce the drag on the downforce producing wings. So, like pretty much if you think of F1 cars and any car that looks like an F1 car, at the back you have these massive wings, these massive airfoils, and they're great for reducing downforce, but not so great for reducing drag. They produce a lot of drag, which means that when you go on straights, for example, you don't really want all that drag because you want to accelerate as quick as possible. So if you can change the angle of these airfoils, that can reduce the drag. And this is what we're looking at today and the effects of this drag reduction system on the lift and drag productions. Now, just a fair warning, whenever I say lift in this podcast, in this particular podcast, I do mean downforce because no time throughout this podcast is there actually positive lift being produced. There's always negative lift, which is downforce. And I know that I'm probably just going to say lift a bunch of times by accident because I've said lift probably 3 billion times in my life by now. So old habits die hard. Just when you hear lift, make sure you understand it's downforce. So if I say it's a lift coefficient of 2, it means a downforce coefficient of 2. Okay, so let's move on to this paper. It's called Aerodynamic Study of a Drag Reduction System and its Actuation System for a Formula Student Competition Car. So drag reduction systems, or DRS systems, were introduced in Formula One in 2011, and it allows the rear wing flap to be placed at the horizontal position at certain locations on the track when the driver is 1 second behind the driver in front. As a result, the aerodynamic drag is reduced by about 20% and increases the possibility of overtaking. An 83% reduction in aerodynamic drag is achieved for a free stream flow test with multi-element rear wings, while a ground effect tested multi-element front wings and it achieved 70% reduction. So what does this mean? Depending on where the wings are, whether it's like very close to the ground or far away, and it's obviously multi-element, which means that there is more than one airfoil. Typically how drag reduction systems work, or just airfoils in general, these downforce systems, you have one airfoil, then behind it you have another airfoil, then behind that one you have another airfoil again, and you might have more depending on the competition. So these airfoils you want to make straight, so instead of being at an angle of attack, you want them to now go straight, and by having them go straight you often reduce the drag. So if the wings are in the ground effect situation, they were able to reduce the drag still by 70% by changing the angle to a neutral position instead of putting them at quite a severe angle attack. So together, these two systems contribute to a 53% reduction in aerodynamic drag created by the car, the front wings and the rear wings. A similar application for DRS, drag reduction system, can be done for a Formula Student competition car, leading to lap reduction times of around 1.5 seconds tested on a track covering 30 laps. Based on a broad research perspective, the application of some high-lift wing profiles are very common. For example, the profiles Epler 423, S1223, FX74, CL5140 are used due to the higher lift coefficients in flows with a low Reynolds number. And this is actually very difficult to do. The reason why is because when you have a low Reynolds number, it literally means that the flow has not very much energy. The boundary layer, let's say we have a regular wing. Let's put it upside down, so we're going to be producing downforce. I'll get this one right. So we have a free stream flow coming in, and we have a boundary layer forming over the suction side, sorry. The flow near the wall is going to be quite slow. What that means is when you have adverse pressure gradients, which you always get on wings producing lift or downforce, that's going to allow the flow to separate much earlier, much further upstream on the airfoil than what you'd like. That means a lot of the airfoil will be stalling. That results in a reduction in lift. So to get a airfoil that can produce so much lift or downforce with low Reynolds numbers is quite difficult to do, but there are a bunch that have been worked on. For example, Epler 423 is very common, and S1223, that's quite common. So to obtain the highest lift coefficients without boundary layer separation, it is necessary to use a fast pressure recovery method, such as a Stratford recovery or concave recovery. Unlike convex pressure recoveries, concave pressure recoveries reaches a very high adverse pressure gradient at the beginning of the pressure recovery, causing the bandulae to be in constant imminent separation. So what does this mean? It means that, so coming back to this picture here, again, if you're just listening to this, you can go to our YouTube channel and watch this. If you are on Spotify, you can also see the video as well. And you can also download this paper in the link in the description. It's open access and you can find it there. So when we have an airfoil and the bandulae is coming over it, to allow the airfoil to continually produce a lot of lift at even low Reynolds numbers, we often want to have the bandulae always teetering on separating. So even at the almost leading edge, the bandulae is very close to separating, but the curvature of the airfoil is just enough to keep it attached. So we're like really pushing the system to the greatest limits. They say though, however, because the bandulae is so thin and sensitive, any disturbances causes the maximum lift coefficient to be greatly reduced. So in other words, because we're teetering on this point where the flow is almost separating, a slight deviation from its optimal conditions can result in the bandulae separating over a portion of the airfoil. That results in a lot of lift being reduced and a lot of drag being produced. So another disadvantage of these types of airfoils is the sudden drop in lift once the profile exceeds the maximum angle of attack, as I mentioned there, because we're teetering on this stall angle of attack or this stall situation. It's very easy for it to stall under suboptimal conditions. So these are these fast pressure recovery profiles. So using numerical simulations and a criteria of a low Reynolds number, high lift coefficient, and a good efficiency between the lift coefficient and aerodynamic drag, the best wing profile for the Formula Student car was found to be the S1123 profile due to its lift and aerodynamic drag ratio. Due to geometry restrictions implemented in the Formula Student regulations, such as the trailing edge of the profile must have a minimum rounding radius of 1.5 millimeters, as sharp edges are not allowed for safety reasons. Further improvements to this S1223 wing profile were made to implement in this Formula Student car. This profile was chosen after comparisons with other profiles due to its high lift coefficient for the Reynolds numbers between 200,000 and 300,000. And just as a note, this is around the transition range point for a boundary layer. For the case of the Formula Student track car, it is important to have a multi-element system. So as I mentioned, multi-element systems are when you have more than one element in an airfoil setup. So you have maybe 3, for example, here, or even more. You can have 5, 10, whatever. Now, interestingly, the basic parameters to consider when designing a multi-element wing profile are the angles of attack and the gap between the main profile and the flaps. In order to achieve a highly efficient design, one guideline by McBeath indicates that the gap and overlap values should stay between 1 to 4% and 1 to 6% of the profile chord size, which leads to the optimization of the larger angle of attack. So what does this mean? So it means that the distance between one airfoil and where the other one starts, there's obviously going to be some sort of overlap. And that distance and the height here, you can find different benchmarks that you should use to optimize the lift being produced or the downforce being produced by the system. And here they're just saying between 1 and 4% and 1 and 6% for the gap and overlap ratios, respectively. So why is this important? I should actually mention this a little bit more. The reason why is because the flow coming from one airfoil, I've actually drawn this a little bit poorly, and I'm going into it a little bit later. But anyway, the flow going over one airfoil will now go over the other airfoil and be redirected. So now you can get this entire system producing a lot of lift. So if we were to take just this third element, for example, which is at a very severe angle of attack, let's say it's at, I don't know, maybe 60 degrees, if you were to have a regular airflow hitting it straight on, that's definitely going to stall because it's just such a massive angle of attack. However, because it's behind a second airfoil, the air coming from the second airfoil is actually directing up. So now the actual angle of attack, the effective angle of attack between this third element and the flow it sees is much less than 60 degrees. So that's why the flow can stay attached and the airfoil will still produce a lot of good lift. So this work that we're looking at now aims to numerically simulate the structural and fluid dynamics for a fully functioning active drag reduction system using CFD. So let's look at the profiles of this wing. I'll zoom in a little bit so you can see them a bit better. So figure 2 shows the simple profile, a multi-element profile, a wing without the actuator, and a wing with 2 actuators. So let's look at this here. Based on the literature review, the geometry of the rear wing will be designed with the S1223 profile. What I can tell you about this is that it's fairly thick at the maximum thickness occurs at about 20% chord, and then it tapers off very quickly, and the trailing edge is very thin. So in order to achieve an efficient design, a vertical gap of 3.8% and a horizontal gap of 5.2% of the profile chord were used to create the multi-element profile. So as I mentioned, the distance between the trailing edge of one airfoil and the leading edge of the next one is actually negative 5.2% of the chord of the upstream airfoil. So there's actually quite a lot of overlap here. And then the distance between the one airfoil vertically and the other airfoil is 3.8%. So additionally, angles of attack between 4 degrees and 5 degrees for the main element, and between 28 degrees and 32 degrees for the second element or flap 1, and 60 degrees and 65 degrees for the third element or flap 2 were used. Now I want to note just how rapidly these angles of attack do change. So the first element, the angle of attack is only 4 or 5 degrees. It's very shallow. But the second element is 28 degrees to 32 degrees. So it's very sharp. And again, if you were to put even this airfoil in a free stream flow, and the angle of attack was actually 28 degrees, it would definitely separate the flow. And then the third element, which is 60 to 65 degrees, that's even worse. But because they're all working in unison, the flow coming from one airfoil hits the second airfoil, and it's redirected so that the effective angle of attack is actually much lower than 28 degrees or 60 degrees. So the downstream airfoil can handle it. So the dimensions of the wings were defined taking into account the regulatory restrictions of the Formula Student rules. Thus, a chord length of 320 millimeters was defined for the main wing, with a 40% reduction for the second element and a 40% reduction for the third element. I'll zoom out a little bit here and let's move on. So let's talk about the CFD setup. So the S1223 multi-element profile is studied in first of a 2D domain just to see its performance without any car around or without any actuator or whatever. And the dimensions of the box were 20 meters long and 10 meters high. In this case, as the aerodynamic analysis is only performed on the rear wing, isolated from the rest of the vehicle, the dimensions were defined through the minimum chassis length established in the Formula Student competition regulations. Due to the complexity of the chosen wing profile, actually, I should probably revisit this. So they said that the minimum chassis length of a vehicle in Formula Student is 1,500 millimeters. So based on that size, you can now make a domain for your CFD and place your vehicle a certain distance in there, and you can just use regular rules of thumb to say, okay, well, the distance between the inlet to the front of the car should be, I think it's 4 times the length of the car, and then the distance between the rear of the car and the outlet should be, I think it's 6 times the length minimum. This is the rule of thumb. And then you have different heights as well. Like, so the top of the domain should be a certain height from the car, etc. So you can just use these general regulations to help define your box. So they say here, due to the complexity of the chosen wing profile, the virtual wind tunnel was, the CFD wind tunnel was designed with a length 4 times longer than the car from the front and 8 times the length of the rear. Sorry, 8 times, not 6 times. It should be an 8 here. So the wing was centered in the middle of this virtual wind tunnel to increase the ability to capture the turbulent flow behavior caused by the wing. So let's talk about this approach and whether this is good or not. So they said that if you have your box here, and this is your CFD box, your domain, right in the middle, they have their wing. So I'm not going to draw all of it. I'm just going to put this here just as an example to represent all of it. So that is implying then that the distance between the ground and the wing is the same as from the top and the wing. Is this a good idea? If the box is really big, yeah, it's fine. It doesn't matter. If the box is a little bit smaller, which you may do to reduce the number of cells you need, then that may not be such a good idea, because what happens is the flow comes over the wing and then it gets redirected up because this is producing downforce. If this wing was producing lift, then you have the opposite thing occurring where the flow will be going down after the trailing edge. But in this particular case, it's going up. So because below the wing, not much is really going to be going on here. You can probably put this closer to the wall to then move it away from this top surface to allow the flow coming off of the wing to develop properly or better and not hit this top part. Because depending on the boundary layer conditions you put on here, which is usually going to be a symmetry plane or whatever, it's going to hinder the development of this wake, which will then impact the upstream airfoil and affect its flow conditions as well as performance. So depending on how big the domain is, you can move this airfoil a little bit closer to the bottom to allow the wake from it to develop properly. And to determine that, you just need to either use rules of thumb or investigate it yourself. So the Reynolds numbers was 1 million, which for this wing resulted in was 1 million, which came from this wing with a chord of 1 meter. Now we talk about something quite interesting. So they say here, the atmospheric free flow simulations had a very small turbulence intensity, and they usually have, so they're saying in real life atmospheric conditions, the turbulence intensity is approximately 0.1%. Now, I don't know where they're getting that value from, because generally the rule of thumb is about 5% to 10%, and that's pretty standard. It could be less, could be more. And to give you an idea, pretty much any time you go outside, there's going to be some sort of wind. And depending on where you are with the buildings around or trees or whatever, or hills, there are going to be changes in, there are going to be disturbances. And those disturbances are far more than 0.1%. So I don't know where they're getting that value from. Maybe one track that they know of might have logged that because it's, I don't know, sheltered or something, I don't know. But 0.1% is almost never the case. That is the case for an airplane flying at 30,000 feet, but not like on the ground. So experimentally, let's move on. Experimentally, it is verified that lower values of this free stream velocity, this turbulence density level, don't affect the lambda transition. So they're saying that using lower turbulence densities are okay, but I would argue that probably a higher turbulence density is probably better here, and also would probably help, because the high turbulence density level will increase the angle of attack that you can push your airfoils to and still produces lift. So the turbulence model chosen to develop the rear wing study was the SST gamma theta model, which I am quite a fan of as well. And this is due to its adequacy over other models used to analyze the behavior of the boundary layer for low Reynolds numbers, which is the case here. This model also has been identified to provide more reliable results than, I'm guessing, like K omega or K epsilon, clearly identifying the flow transition behavior for low Reynolds numbers, as well as for low and high angles of attack. So in this present project, the mesh quality for each simulation was analyzed through its asymmetry and orthogonality, as well as the residuals. So what is this? Asymmetry and orthogonality and residuals, they are different. The asymmetry and orthogonals are for the mesh itself, whereas residuals is for the convergence of the simulation. That's during the solving stage. The asymmetry and orthogonality can affect the accuracy of the information that is going from one cell to another, because you may, depending on how the cells are aligned, and the equations will then have certain errors associated with them, including even round-off errors, which when you go to very fine meshes, that can even affect the results a little bit. Usually not, but sometimes. But anyway, the unstructured mesh was used with tetrahedral elements, except for prismatic elements with the inflation layers. So what does this mean? So let's go down to this figure here. They have over the boundary of the surface of the actual airfoil, they have a boundary layer mesh, which is just a bunch of cells in a very nicely uniform fashion growing out into the free stream. And around it, they just have all these tetrahedral cells. So they're like kind of like pyramid cells kind of thing. If you don't know what they look like, they're kind of like pyramids. And they say that Tetrahedral elements were used because they present the fastest way to generate a computational mesh with the least amount of memory required. And that's a big deal because some like cells take up a lot of memory. And generally speaking, it's about 1 million cells for every gig of RAM you have for a Navier-Stokes solver. If you use lattice Boltzmann method, then that does change depending on the software you're using. You can get like, I think the best I know of at the moment is about 16 million cells, or 60 million boxes, I should say, for every gig of RAM. So moreover, I digress. Due to the complex shape of the wings, with the flaps and the drag reduction actuator, the unstructured mesh allows a better study of these areas. So why is that? It is because these unstructured meshes, they can mold themselves to the geometry better, and they can also handle more complex flows. For the 3D studies, in order to increase the mesh density near the trailing edges, the areas of worst asymmetry and mesh orthogonality, the surface elements associated with the trailing edge of the wing profiles were dimensioned with 0.0008 meters with a volumetric maximum growth rate of 1.1. What does all of this mean? So the first thing they say is in the trailing edges of the airfoils, this is where the worst asymmetry and mesh orthogonality occur. So why is this? The reason why is because you have a sharp trailing edge. In this case, it's even rounded, but still it's quite sharp. And you have these cells coming in, and then at the trailing edge, they have to meet. So then what happens here? You often then get these cells being squished and trying to just get mashed in here. That results in a lot of skewness, a lot of asymmetry, and a lot of orthogonality. What this means is just poor cell meshes. You get a lot of weird looking cells, which then result in a lot of errors that propagate through the borders of these cells. So what they're saying is they're focusing on this area here. And also they say that the volumetric rate of maximum growth is 1.1. So what this means is the boundary layer mesh that they have around the airfoil, including the trailing edge here, they're only allowing this to grow at a maximum of 1.1. So that means that the second cell above can only be 1.1 times the height of the first cell, and then so on. So the third cell can only be 1.1 times the height of the second cell, and so on. This allows the mesh not to grow too quickly, so you won't get as much funky looking cells in the trailing edge section. So that's a good thing to do. So let's talk about the results. So the S1223 profile in 2D. For the 2D simulations, an analysis of mesh properties was made by changing the numbers of elements and the evaluation of the asymmetry and orthogonality for 3 angles of attack, 0 degrees, 10 degrees, and 12 degrees. Figure 5 presents the impact of increasing the number of elements on the lift and drag coefficients using the coarsest mesh as a reference. So they have 3 different graphs here, and they show just the relative error between the higher meshes, so the more refined meshes, and the coarsest mesh, which had only 112,000 elements, 113,000 elements, sorry. And what they found was, as you'd expect, generally speaking, as you increase the number of cells, you get a like a plateau in the results, and that means that you get a mesh independence going on. Now, interestingly, as you get to 12 degrees, though, the difference between the plateau sort of suddenly jumps up. So this means is when you get to 1 million cells for this entire situation, this entire CFD simulation, that is significantly different to the results that you get when you have only 700,000 cells and 560,000 cells and 450,000 cells. So for some reason, something is going on here at 12 degrees, and I think it's to do with flow separating, and that is to be expected. At other angles of attack, you do get a bit more of a plateau going on, and you can argue that it's fine because it's within like 1% error. But at 12 degrees, it sort of jumps up to like about 2%. So it's getting a little bit worse, and just depends on what you want to achieve. Here they say, results suggest that increase the number of elements above 350,000 and provide small changes on the lift and drag coefficients. Therefore, this mesh was selected as the basis for the profile analysis, since it uses low computational requirements and provides good quality. So again, if you want to get good CFD results, you should probably go much higher than that. This mesh dependency study was showing that even at 1 billion cells, there was still significant changes, and you should probably go higher than that again just to see what's going on. But because they just want to reduce their computational cost, they're going for a lower quality mesh, and they're just dealing with the errors and saying, okay, well, the errors are going to be 2, 3, 4%, and that's all there is to it. So let's talk about this multi-element profile for this S1223. So they say the best aerodynamic results were obtained for a lift coefficient of 3.4 and a drag coefficient of 0.12. And this resulted from a configuration where the first element was 4 degrees, second element was 28 degrees, and the third element was 60 degrees. So is this good? The lift coefficient is really good because a regular airfoil, just a one element airfoil, typically will result in a lift coefficient of around 1.5 or so. However, the drag coefficient will be about 0.2, maybe 0.15. So here we have a lift coefficient about twice as much as just a regular airfoil, but the drag coefficient is about 6 times as high. So that often happens. You get a much greater increase in drag, even with the increase in lift. However, in this particular case, it's valid. Now, one thing that's interesting to me is in table 2, they show the effects of the different angles of attack for the different flaps. In 2D, I should remind you, and their effects on the lift and drag coefficients. So interestingly, when we have the main wing at 4 degrees, then the second element at 28 degrees, then the third element at 60 degrees, we get really nice results. The lift coefficient is 3.4, the drag coefficient is 0.122. But if we increase just the angle of attack of the second element by 1 degree to 29 degrees, all of a sudden the lift coefficient of the entire system drops dramatically. It goes to 2.1, and the drag coefficient increases a lot to 2.9. So to 0.29. So that shows that this system is very sensitive. Now, something that should be mentioned is that this could also be an artifact of the CFD not being accurate in this zone. However, I think that it probably will be accurate to some extent, like maybe not these changes would be so dramatic, but it would be significant at this around this angle of attack. So it shows just how fiddly this system is to just slight changes in the flow. So this second element dramatically can change the lift coefficient, and only if you have a small change in conditions, upstream conditions. So what does this mean in real life? It means that if you're driving your little Formula Student car around and upstream you have another car, its wake will dramatically affect your drag or your downforce production at the moment, because the wake is going to hit your wings and it's going to destabilize the flow a lot. It shows that just a small change angle attack has a massive reduction. It's like about 30-40% reduction in lift. So that's not good. However, other angles of attack, the system seems to be a lot more stable. So this might just be a fiddly situation where they need to refine this system just for this particular situation here. So they say they have a plot of the velocity going over this 3-element system, and they show that the maximum speed obtained was 59.2 meters per second, which was at the leading edge of the first element, and then it decreases after that. Now, this is a good indication of how much energy is in the flow and how much more lift you can get out of the flow. So the first wing is subject to quite a fast-moving flow. The second wing, not so much, and then the third wing, even less. So it shows that once you get downstream, you have taken more and more energy out of the flow, which means that you can't really get as much lift for subsequent elements. So that means that if we were to put more elements on here, we probably wouldn't get nearly that much lift out of it. So it's probably a waste to put more elements on there. You'll probably get a lot more drag out of it, but lift not so much. So let's talk about the 3D setup now. The rear wing has a lift coefficient now of 1.28 and a drag coefficient of 0.43. So it went from 3.4 in a 2D situation to only 1.29 now in a 3-dimensional situation. And the drag coefficient jumped by a factor of almost 4. So figure 8, they say it can be seen that the end plates to this structure fulfill their role by preventing the appearance of large wingtip vortices on the edges of the wings and delay their appearance, thus improving the ability to generate negative lift of the 3 elements belonging to the rear wing. However, Vortices are formed on the upper and lower surfaces of the end plates with a vorticity that is 33% lower than those generated without the end plates. So in other words, the end plates do make a massive difference to the vorticity. As we know, they reduce the strength of the vortices, which also reduces the drag, but also increases the lift. Why is that? Oh, sorry, the downforce, I should say. Why is that? The reason why is because let's say we have a wing. We're looking at it from the top. So we have the free stream flow coming in, and we have a wingtip vortex coming, and it's coming over the top here, and one on the other side too. What these wingtip vortices do is over the top of the wing. So now let's look at it from front on. We have these vortices coming over. They push the flow down near the edges, near the wingtips. So that means that the effective angle of attack in these zones is lower. If the angle of attack goes down, so does the lift coefficient. So by putting the end plates here, we block off these vortices, and they can no longer come around and reduce the effective angle of attack, which means they don't reduce the effective lift that's being produced at this region, which means you get a higher lift being produced. So what about the multi-element system with the 3D actuator? So they want to change the angle of attack of these wings when we're on the straights to reduce the drag. They say the actuator of the drag reduction system is responsible for 9.5% reduction in the lift coefficient and an 8.3% reduction in the drag coefficient compared to the rear wing without an actuator. The rear wing plus the drag reduction system has a maximum lift of 1.16, which is set so they say that, okay, we can't go higher than that. And the maximum drag coefficient is 0.397. Now, figure 9 represents the speed and pressure generated on the rear wing with actuators. It can be observed that the linear actuator causes a deceleration of the flow around it, generating a very low speed and pressure zone in the immediate vicinity of the actuator. The vortex on the upper surface of the end plate has the same behavior as presented in figure 8. However, the vortex generated on the lower surface of the end plate has a larger core, but circulates with a lower vorticity. I should mention that vorticity is not the be-all and end-all to a vortex. In fact, it may not even indicate that there may not even be that there is a vortex there. They could just get vorticity from the surface. But higher vorticity means that if there is a vortex there, it's more concentrated. If there isn't a vortex there, there's still a concentration of like flow circulating around a little bit. And that means that there is often going to be flow around that being induced as well in this direction as well. The higher the vorticity, the more it's going to pull more flow from around it into it and make it circulate around as well. So what about when we put the DRS system on? So we change the flaps angles from 5 degrees, 28 degrees, and 60 degrees to 0 degrees. So when the DRS system is operated, the flaps rotate until they reach an angle of attack of 0 degrees. When opening these flaps, the DRS system provides a 78% reduction in the drag coefficient while reducing the lift coefficient by 53% compared to when the flaps are at their operating condition. The rear wing with the open DRS system generates a lift coefficient of 0.54 and an aerodynamic drag coefficient of 0.086. So that drag coefficient is actually really nice. Like 0.086 is pretty decent. The lift coefficient is still very high still. It's 0.54. So getting that much lift out of this system with such a low drag coefficient is quite good. But why do we get such a high lift still? The reason why is because these airfoils are not symmetrical. They're cambered. So they are obviously going to produce a downforce, even at 0 degrees angle of attack. To get a 0 degree angle of attack, you need to put, a 0 lift coefficient, you need to put the angle of attack very negative. I'm not sure the exact angle of attack. It might be 2-3 degrees. But with that, you're going to get an increase in the drag coefficient as well. So here is the best situation to get the lowest drag possible. So in figure 11, it presents the path lines over the closed and open DRS system. When the drag reduction system is closed, it can be observed with a higher vorticity near the end plates, which is propagated behind the rear wing, which increases the drag. So in other words, we get a huge vortices being produced, and that's indicative of high lift because we have a very low pressure on the bottom surface and very high pressure on the top surface. Even with these end plates, the flow wants to come around and just whip up and create these vortices. Also, I should say whip down because it's producing downforce. When the DRS system is open, though, the flow is less affected by the vorticity near the end plates particularly near the midsection of the rear wing. It can be seen that the straight path lines interact between the two upper flaps is lower when the DRS system is open as expected. So again, because the DRS system is open, the flow is not being channeled nearly as much, like it's not being redirected to other elements on the system. So the flow is not going to be hitting all these different elements in succession, which also reduces the drag. So that's the end of this podcast. We covered the effects of, well, we covered actually first the setup of a 2D 3-element downforce producing system. We then looked at a 3-dimensional system and the effects of opening and closing these flaps to increase or reduce the downforce production and the drag. So make sure to like, subscribe. And if you want to get better at CFD yourself and or theory like this, check out our courses in the link description. And if you want to make your experiments 2 to 4% more accurate, check out the MSU Hawk. It's an instrument we make, which makes your experiments that much more accurate. And that's just on a regular day, by the way. Between days, weeks, months, seasons, it actually makes your experiments even more accurate by about 15%. The reason why it does this is because the density of air changes throughout the day and between days, between weeks, between seasons, and between months. That's because the temperature changes, the pressure changes, and the humidity changes. And most researchers do not take account of these changes. So that means when you take your experimental measurements, these errors are going to be in there. So when you go, when you take your measurements and you go process them, you'll see that they don't really line up properly, and there are going to be little errors that you don't even know about, and you won't find trends that are there, and you might find trends that aren't actually there. So you will start reporting trends that don't actually exist. So that makes your experiments far more inaccurate, and you can't really trust them very much. Also, when you go to your CFD, it means that when you try to validate your CFD data, with your CFD with your experimental data, they're not going to line up properly because your CFD is going to have a very different density to your experiments, and your experimental data is already off the charts anyway, like it's going up and down, whatever, based on the changes in the density. So this MSU Hawk gets rid of those errors for you, makes your experiments far more accurate, makes your CFD validation much easier. So you check that out in the link description. I'll see you in the next podcast. Peace out, amigos.